For centuries, humans have imagined the universe as something that must have an edge, a distant boundary where space simply ends. It feels intuitive. Every room has walls, every land has borders, every ocean has a shoreline. And yet, when science turns its gaze outward toward the largest structure that exists, intuition begins to fail. Modern cosmology tells us that the universe is expanding, that galaxies are rushing away from one another, carried along by the stretching of space itself. But expansion raises a deeper and far more unsettling question. What is it expanding into? Is there an outer edge, a cosmic cliff beyond which there is nothing, or is the universe structured in a way that makes the very idea of an edge meaningless? At the heart of this mystery lies the concept of the universe's shape. Not its appearance, not where galaxies are located, but the underlying geometry of space itself. Scientists describe three broad possibilities. Space could be positively curved like the surface of a sphere. It could be negatively curved like a saddle stretching infinitely outward. Or it could be flat, obeying the familiar rules of Euclidean geometry taught in classrooms. Parallel lines never meet. Triangles add up to 180 degrees. Space feels ordinary. Surprisingly, every precise measurement we've made so far points to the same conclusion. On the largest observable scales, the universe appears to be flat. Light travels as if space is not curved. Distances behave as expected. The geometry checks out again and again. But flatness does not answer the most haunting question. Does flat mean infinite? At first glance, it seems obvious. If space is flat, shouldn't it stretch on forever? Yet mathematics offers a far stranger possibility. Space can be flat and still be finite, just as a video game world can feel endless while secretly looping back on itself. The universe could be flat, but wrapped in ways that hide its true extent. This leads to an unsettling idea. We may be living in a universe with no edge at all, not because it is infinite, but because space connects back onto itself. Travel far enough in one direction, and you might, in principle, return to your starting point. No boundary crossed, no wall encountered, just an unbroken continuity of space. If this is true, then the universe is not a vast open plain, but a carefully structured shape whose global form is invisible from any single location inside it. The cosmos would have no center, no edge, and no privileged viewpoint. Every observer, everywhere, would see the same illusion of endlessness. To test these ideas, scientists turn to the oldest light in existence, the faint afterglow of the Big Bang itself. This ancient radiation carries subtle patterns, frozen echoes of the universe when it was young. If space loops or folds in hidden ways, those patterns might repeat. The same structures could appear more than once in different directions, like reflections in a cosmic hall of mirrors. So far, the evidence remains elusive. The universe appears smooth, flat, and vast beyond comprehension, but appearances can deceive. The deeper scientists look, the more they realize that understanding the shape of the universe is not just a question of size or distance. It is a question about the very rules that govern reality. And if the universe truly has no edge, then the most profound boundary we face may not be physical at all, but conceptual, the limit of how the human mind understands space, infinity, and existence itself. If the universe truly has no edge, then our instincts about space are deeply flawed. To grasp why, scientists had to abandon everyday intuition and replace it with geometry on a cosmic scale. The key lies not in what we see, but in how space behaves when stretched to its limits. To understand this, cosmologists perform thought experiments. Imagine beings living on the surface of a vast sheet. From their perspective, everything appears flat. They can walk in straight lines forever without encountering a boundary. Yet if that sheet were suddenly folded into a torus or wrapped back onto itself, those travelers could eventually return to their starting point without ever turning around. No edge would be encountered, yet the space would still be finite. This is the unsettling possibility scientists consider for our universe. Space may look flat locally, just as Earth looks flat beneath our feet, but globally, its structure could be far more complex. The universe might be flat yet topologically closed, meaning it connects back on itself in dimensions beyond ordinary perception. The challenge is that we cannot step outside the universe to look at its shape. We are embedded within it. Every observation must be made from inside the system we are trying to measure. This makes the problem uniquely difficult, unlike measuring the shape of a planet or a galaxy. So researchers search for indirect evidence. One of the most powerful tools is the cosmic microwave background, the ancient radiation released when the universe was only hundreds of thousands of years old. This radiation forms a nearly uniform glow across the sky, but it contains tiny temperature variations, faint ripples that preserve information about the universe's geometry. If space loops back on itself, those ripples could repeat. The same pattern might appear in multiple directions, separated across the sky. Astronomers have searched for these repeating circles, ghostly echoes of the same region of space seen more than once due to cosmic wraparound. So far, no clear repetitions have been found. But absence of evidence is not evidence of absence. The universe may simply be larger than the region we can observe, hiding its true topology beyond our cosmic horizon. Light has only had a finite amount of time to travel since the universe began. Anything beyond that limit remains fundamentally unreachable. This introduces a profound limitation. The observable universe may be only a small patch of a much larger whole. If the universe loops on scales larger than what light has crossed, then we may never detect the pattern. The universe could be finite, flat, and closed, and we would have no way of knowing. This uncertainty raises a disturbing implication. The ultimate shape of the universe may be unknowable in principle, not just in practice. Even with perfect instruments and infinite patience, we may be trapped inside a cosmic structure whose full form lies forever beyond observation. In this sense, the universe does not merely lack an edge in space, it may also lack an edge in knowledge, and that realization forces a shift in perspective. The question may not be, do we live at the edge of the universe? But rather, are we capable of recognizing an edge at all? As scientists push deeper into this mystery, the boundary between physics and philosophy begins to blur. The shape of the universe is no longer just a technical problem. It becomes a mirror reflecting the limits of human understanding and a reminder that the cosmos may be far stranger than even our boldest theories suggest. As the search for the universe's shape continued, scientists realized that geometry alone was not enough. Even if space appears flat and endless, something deeper governs its behavior, something that determines whether the universe will expand forever, slow down, or eventually tear itself apart. That governing factor is energy itself, spread thinly across the vastness of space. For much of the 20th century, cosmologists assumed the universe's expansion was gradually slowing. Gravity, after all, pulls matter together. Given enough time, it seemed reasonable that expansion would weaken, perhaps halting entirely. In some models, the universe would reverse course and collapse inward in a catastrophic implosion. In others, it would coast forever, expanding at a diminishing pace. But observations at the end of the 1990s shattered these expectations. Distant galaxies were not slowing down, they were accelerating away from each other. This discovery forced scientists to confront a previously unknown component of reality, a form of energy embedded within space itself, exerting a repulsive pressure that overwhelms gravity on cosmic scales. This phenomenon became known as dark energy, not because it is sinister, but because its nature remains profoundly obscure. Dark energy changes everything about the universe's fate and its geometry. If dark energy dominates, space does not merely expand, it stretches faster and faster, carrying galaxies beyond each other's reach. Over time, even nearby clusters may vanish from view, swallowed by the growing gulf of space. In a flat universe dominated by dark energy, there is no edge to approach and no center to locate. Every observer sees the same thing, distant galaxies rushing away, cosmic structures dissolving into isolation. The universe, becomes a place where emptiness grows more powerful than matter itself. This raises a troubling question. If the universe is flat and expanding at an accelerating rate, could there be regions that are forever inaccessible, not because they are beyond an edge, but because space itself pulls them away faster than light can bridge the gap? The answer appears to be yes. Cosmologists describe this limit as a cosmic event horizon. It is not a physical boundary you could touch or see. Instead, it is a moving frontier defined by time and expansion. Beyond this horizon, events can never influence us, no matter how long we wait. Light emitted there today will never reach Earth. Those regions might as well not exist, at least not for us. This creates a strange paradox. The universe may be infinite, yet functionally finite. Vast domains of reality exist that are forever cut off, not by walls or edges, but by the relentless stretching of space. Even more unsettling is the realization that this horizon is shrinking in a relative sense. As time passes, fewer galaxies remain visible. The night sky of the far future will be darker, emptier, lonelier. Astronomers of distant epochs may look up and see only their own galaxy, surrounded by apparent nothingness, unaware that a vast cosmos once lay beyond. In such a universe, the idea of an edge becomes meaningless. There is no cliff to fall from, no boundary to cross. Instead, there's a gradual erasure of connection, a slow severing of cosmic relationships. Yet this accelerating expansion also hints at the universe's earliest moments. To explain why space appears so flat today, scientists propose a brief but violent phase shortly after the universe's birth: cosmic inflation. During this fraction of a second, space expanded exponentially, smoothing out any initial curvature. Inflation explains why the universe looks flat, even if it began with some curvature. It also suggests something even stranger. Inflation may not have ended everywhere at once. Some regions could still be inflating, giving rise to a vast ensemble of disconnected universes, each with its own properties, laws, and histories. In this view, our universe is not the whole of existence, but a bubble within a much larger cosmic structure. The edge of our universe would then be not a place in space, but a boundary in time. The moment inflation ended locally and allowed stars, galaxies, and observers to form. If this is true, then asking whether we live at the edge of the universe misses the point entirely. There may be no single universe with a definitive boundary. Instead, reality could be a mosaic of expanding regions, forever isolated from one another, and we are confined to just one. This possibility transforms the question from one of geography to one of perspective. We are not explorers standing near the edge of a cosmic map. We are inhabitants of a region whose full extent may be permanently hidden, not by distance, but by the fundamental behavior of space itself. The universe does not need an edge to feel infinite, and it does not need infinity to feel unknowable. The deeper scientists look, the clearer one truth becomes. The limits we encounter may not belong to the universe at all. They may belong to us. As scientists push deeper into the question of whether the universe has an edge, they encounter a more unsettling realization. The greatest boundary may not lie in space, but in knowledge itself. Even with the most advanced instruments ever built, there are limits imposed not by technology, but by the structure of reality. To understand this, cosmologists turn their attention to the cosmic microwave background, the faint afterglow of the universe's earliest moments. This ancient radiation fills all of space, arriving from every direction with extraordinary uniformity. It is the oldest light we can ever observe, a snapshot of the universe when it was only a few 100,000 years old. If the universe had an edge, or if space curved sharply on large scales, subtle distortions would be imprinted in this background light. Hot and cold patches would arrange themselves in patterns revealing a boundary, a wraparound, or a curvature that bends back on itself. Yet what scientists see instead is remarkable simplicity. The temperature variations in the cosmic microwave background are tiny and evenly distributed. Over immense distances, space appears geometrically flat to astonishing precision. This means that parallel lines never meet, triangles add up to 180 degrees, and the universe follows the familiar rules of Euclidean geometry, not just locally, but across billions of light years. But flatness does not imply simplicity. A flat universe can still be finite or infinite. It could extend forever, or it could loop back on itself in subtle ways, forming a shape so vast that its repetition lies far beyond what we can ever detect. Space could be like the surface of a video game world that seems endless to the player, yet secretly folds back when you travel far enough. Scientists have searched for evidence of such cosmic repetition, identical patterns in the microwave background, that would suggest light has wrapped around the universe more than once. So far, none have been found. Either the universe is infinite, or its size exceeds the observable region by an unimaginable margin. This brings us back to a haunting conclusion. The observable universe is not the universe itself. What we can see is limited by the speed of light and the age of the cosmos. Beyond a certain distance, space has expanded so much that light has never had time to reach us. These regions are not merely distant, they are causally disconnected. They exist in the same universe, yet are forever beyond interaction. This creates a strange illusion of centrality. Wherever you stand in the universe, you appear to be at the center of an expanding sphere of observable space. Every observer sees galaxies receding in all directions as though they occupy a privileged position. But this is a trick of perspective. There is no true center, only countless local viewpoints, all equally valid. If the universe has no center and no edge, then what does it mean to ask where we are? The answer is unsettlingly simple. We are nowhere special. Yet this lack of specialness carries profound implications. In a universe without boundaries, laws must be universal. The same physics governing galaxies billions of light years away must apply here as well. The flatness of space ties distant regions together in a shared cosmic order, even if they can never communicate. But there is another layer to this mystery. Flatness appears fragile. In theory, even a tiny deviation in the early universe should have grown dramatically over time, producing a universe that curves sharply or collapses quickly. The fact that space remains so close to perfectly flat suggests an extraordinary fine-tuning, or a mechanism that actively enforces it. This is where inflation returns to the story. During inflation, space expanded faster than light itself, stretching any initial curvature until it became imperceptible. Just as the surface of a balloon appears flatter as it inflates, the universe became geometrically smooth on vast scales. This process did not need to produce a finite universe. It only needed to make any curvature effectively invisible. But inflation may have done more than that. Quantum fluctuations during this explosive expansion may have seeded the structure of everything we see today: galaxies, clusters, and voids. Tiny ripples in energy density were stretched across cosmic distances, later growing into the large-scale structure of the universe. In this sense, the universe's apparent flatness is not an accident. It is a fossil record of its violent birth. And yet, inflation raises disturbing possibilities. If inflation can occur once, it may occur repeatedly. Some regions may stop inflating, forming universes like ours, while others continue expanding endlessly. The result would be a vast cosmic landscape where universes bud off like bubbles in a boiling sea. If this picture is correct, then asking whether our universe has an edge becomes deeply ambiguous. Our universe may have boundaries in time, a beginning and an eventual fate, but not in space. Beyond our observable region could lie not emptiness, but other expanding domains forever inaccessible. We are trapped not by walls, but by horizons. This realization reframes humanity's place in the cosmos. We are not explorers approaching the universe's edge. We are inhabitants of a limited window into a much larger reality, one that may never reveal its full extent. The edge of the universe, if it exists at all, may not be something you can reach. It may be something you can only infer, a boundary defined not by distance, but by the fundamental laws governing space, time, and observation. And that may be the most unsettling conclusion of all. The universe does not hide its edge from us out of malice or mystery. It hides it because by its very nature, we were never meant to see it. The deeper scientists push into the question of cosmic boundaries, the more the idea of an edge dissolves into something far stranger and more abstract. What once seemed like a geographic question, where does the universe end, transforms into a philosophical and physical one. What does it even mean for reality to have limits? At this stage, cosmology collides with fundamental physics. One of the most unsettling discoveries of modern science is that the universe appears to enforce limits on information itself. No matter how powerful our instruments become, no matter how advanced our theories grow, there are ceilings beyond which knowledge cannot pass. These limits are not technological. They are woven into space-time. This realization emerged from black hole research. When physicists studied black holes, they encountered a paradox. If information falls into a black hole and disappears forever, the laws of physics break down. Information, according to quantum mechanics, cannot be destroyed. Yet black holes seem to erase it completely. The resolution to this paradox led to a radical idea. Information is never lost. It is stored on the boundary. The event horizon of a black hole, a two-dimensional surface, somehow encodes all the information about the three-dimensional matter that fell inside. This shocking result suggests that volume is not fundamental. Surfaces are. If that idea is true for black holes, could it also be true for the universe itself? This question gave rise to the holographic principle, the proposal that everything within a region of space may be fully described by information encoded on its boundary. Just as a hologram creates a three-dimensional image from a flat surface, reality itself may emerge from lower-dimensional data. In this view, the universe does not need an edge in the traditional sense. The boundary may not be spatial, it may be informational. What we experience as depth, distance, and volume could be emergent properties, projections arising from more fundamental laws operating on a cosmic surface. The universe may be less like an endless landscape and more like a vast, dynamic computation. This reframes the original question entirely. Do we live on the edge of the universe? May not mean, are we near a wall? It may mean, are we living on a boundary we don't recognize as a boundary? Some physicists propose that the observable universe itself behaves like a holographic screen. Everything we see, galaxies, stars, planets, even ourselves, could be encoded on a cosmic horizon defined by the limits of light and time. This horizon is not fixed. As the universe expands, the observable boundary shifts. New regions enter view, while others slip permanently beyond reach. The edge is dynamic, shaped by expansion and the speed of light, not by physical barriers. Yet this moving horizon acts like a true boundary in one crucial sense. Nothing beyond it can ever influence us. No signal, no particle, no information can cross that limit once space expands too quickly. Those regions still exist, but they are causally disconnected forever. For all practical purposes, they might as well be separate universes. This leads to a profound implication. The universe may be vastly larger than anything we can observe, but reality itself is filtered. We do not experience the universe directly. We experience a projection limited by horizons, and there may be deeper horizons still. Quantum gravity suggests that at the smallest scales, far smaller than atoms, space and time lose their familiar meaning. Distances blur. Causality becomes uncertain. The idea of location itself may dissolve. If space-time is emergent, then edges may be emergent too. In such a universe, asking where the edge lies is like asking where the edge of a shadow is. The shadow depends on the light, the object, and the observer. Change any of those, and the edge shifts or vanishes. Our sense of cosmic boundaries may be a consequence of our position, our physics, and our limitations, not a fundamental feature of existence. And yet, the universe leaves clues. The accelerating expansion of space hints that the cosmos may be driven by unknown forces shaping its ultimate fate. If expansion continues indefinitely, distant galaxies will disappear beyond our horizon, leaving future observers in a dark, lonely universe, unaware of the vast structure that once surrounded them. In that future, the edge will not be theoretical. It will be experiential. Civilizations trillions of years from now may look out into the sky and see only their own galaxy, surrounded by emptiness. For them, the universe will appear small and finite, not because it is, but because everything else has slipped beyond reach. This means we live at a privileged moment in cosmic history. Right now, we can still see the echoes of the Big Bang. We can still map large-scale structure. We can still infer the universe's geometry and origins. The window is open, but it will not remain so forever. The edge of the universe, then, is not a location. It is a moment, a fleeting era in which observation is still possible. As the universe evolves, that edge creeps inward, erasing evidence, narrowing perspective, reshaping reality for future observers. The cosmos is not static. It hides itself over time, which leads to the most unsettling possibility yet. Perhaps the universe always had an edge, not in space, but in accessibility. And perhaps every intelligent civilization inevitably finds itself asking the same question, staring into the same horizon, unaware of how much has already been lost. We are not standing near the edge of the universe. We are standing near the edge of what can ever be known. And that realization forces a final question, one that cannot be answered with telescopes or equations alone, but only with deeper insight into the nature of reality itself. At the deepest level, the search for the edge of the universe becomes a confrontation with the limits of existence itself. After centuries of observation, calculation, and imagination, science arrives at a quiet but devastating conclusion. The universe may not offer an ending we can reach, only one we can approach in thought. The idea of an edge once felt comforting. An edge implies structure, containment, and completion. It suggests that if we traveled far enough, if we were patient and clever enough, we might eventually arrive at a boundary, a final wall of reality beyond which nothing exists. But modern cosmology has steadily stripped that notion away. Instead, we are left with horizons. Horizons are not places, they are conditions. They are defined not by distance, but by time, expansion, and causality. The cosmic horizon marks the limit of what can ever affect us, not because anything stops existing beyond it, but because space itself expands too quickly for information to cross back. This means the universe does not end, it simply becomes unreachable. Beyond our observable horizon may lie countless galaxies, stars, and structures as rich and complex as our own. They are not hidden by darkness or walls, but by the relentless stretching of space. The universe grows faster than light can travel, silently isolating regions from one another. From this perspective, the question, do we live on the edge of the universe, takes on a haunting new meaning. Every observer, anywhere in the cosmos, always lives at the center of their own observable universe, and simultaneously at its edge. The horizon surrounds them in all directions, an invisible boundary beyond which reality continues but forever escapes interaction. There is no privileged location, no cosmic center, no outer rim, only countless observers, each enclosed within their own shrinking window of knowledge. This realization forces us to confront a deeper truth. The universe may be fundamentally unknowable in its entirety. Not because we lack intelligence or technology, but because the laws of physics themselves impose limits on what can be observed, remembered, and measured. Even the most powerful theories, relativity, quantum mechanics, inflation, converge on this sobering insight. Space-time has built-in restrictions. Information cannot travel arbitrarily far. Entropy increases, horizons form, knowledge fades. In time, even black holes, once thought eternal, may evaporate, releasing their final whispers of information back into the universe. And when the last black hole fades, the universe may become a thin, cold sea of particles drifting endlessly apart. In that distant future, the cosmos will still exist, but meaning itself may dissolve. Without observers, without structure, without memory, the universe will continue, silent and indifferent. And yet, here we are, living at a moment when the universe is still visible, when its ancient light still reaches us, when its geometry, history, and laws can still be reconstructed from faint signals crossing unimaginable distances. We are not near the beginning of time, nor the end. We exist during a rare window when the universe can still be known. That may be the true significance of the edge, not a physical boundary in space, but a fleeting boundary in cosmic history, a narrow era in which understanding is possible at all. The universe does not place us at its edge to mock us. It places us there because every conscious being, in every era, must confront the same horizon, the same silence beyond reach, the same realization that reality is larger than comprehension. And perhaps that is the final truth this journey reveals. The universe does not end where we stop seeing it. It ends where our ability to know runs out. Beyond that edge, reality continues, vast, indifferent, and forever beyond grasp. And standing here, gazing into the darkness, we are not explorers at the brink of space. We are witnesses, briefly allowed to see, to question, and to wonder, before the universe slowly closes the window behind us.